is number 313, which is 2011 AB5. And for this problem, we know that at the beginning of 2010, a landfill contained 1,400 tons of solid waste. The increasing function W models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy the differential equation dW dt equals 1 over 25 W minus 300 for the next 20 years. W is measured in tons and T is measured in years from the start of 2010. So the first thing that the problem asks us to do is to use the line tangent up to the graph of W at T equals 0 to approximate the amount of solid waste that the landfill contains at the end of the first 3 months of 2010. So for this, we need a point and we need a slope to get a tangent line. So for our point, we are looking for W of 0, or the amount of waste in the landfill when time equals 0. And time equals 0 is 2010. And at the beginning, it tells us that we have 14,000 tons of waste. And we are wanting the tangent line at 0. That's what we're looking for. So we've got some sort of curve, and we know that it goes through here. And we're going to make ourselves a tangent line. And then if we're only looking at T equals 1/4, if we plug in 1/4, that's going to be pretty close to what the actual amount is. So we're looking for tangent line at 0. So we're looking for dW dt, the slope of W, whenever T equals 0. But here's the problem. We don't have a W to plug in here. There is no T. That W is our amount of waste. And we're looking for the amount of waste whenever T equals 0, which we just found was 1,400. So what we're going to have here is 1 over 25 times 1,400 minus 300. And so we're going to get 1 over 25 times 1,100. And whenever we do that, we are going to get 44. So our tangent line is y minus 1,400 equals 44 times x minus 0. So this is our tangent line here. And what we want to do is we want to use the tangent line, and we're going to plug in 1/4, because if we plug in 1/4, it's going to be pretty close to the actual answer if we were to use the real line that we don't really know. So we're going to plug in 1/4 for our x. I guess really technically I should put a t here instead of an x for that. So 44 times 1/4. And so we get y minus 1,400 equals 11. And we're going to add that 1,400, so y equals 1,411 tons of waste in the landfill after 3 months. Okay. Our next equation asks us to do something. The second part asks us to find the second derivative in terms of W. Use the second derivative to determine whether your answer in part A is an underestimate or an overestimate of the amount of solid waste that the landfill contains. So that problem that I just did, we don't really know whether this graph is concave up or concave down. We do know that the graph is increasing because it tells us that W is an increasing function. If the graph is concave down, then a tangent line would lie above that graph, which would make it an overestimate. If the graph is concave up, the tangent line would lie below the graph, which would make it an underestimate. So we're looking for concavity here. So we're going to start with our derivative, dW dt equals 1 over 25 times W minus 300. And we're going to take the derivative. You may even want to sort of distribute here before you take the derivative. That that 1 over 25 is kind of messing me up. So the 1 over 25 W minus 1 over 25 times 300. 300 divided by 25 is going to give you 12. So if we take our derivative, our second derivative here is just going to be 1 over 25. And so when we take that but when we take that derivative, that 1 over 25, we have to put a dw dt there with it, because we took the derivative of a w, so we must put a dw dt with that problem. So notice up here it says find the second derivative in terms of w. So that means we can't have this dw dt left in our answer. So what we're going to have to do here is we're going to go up here, and we're going to take our second derivative, and we'll have 1 over 25, and then whenever we have dw dt, we replace it with dw dt, because right up here we already knew what dw dt was. It was 1 over 25 w times 1 over 25 w minus 300. So we have 1 over 25 times w minus 300. And so you can put those together if you want, but you can leave it like that if you need to. So you get 1 over 625 w minus 300. And our tangent line is at 0. So if we plug in 0 into this, if we plug in 0, or t equals 0, into this equation, we're going to have d squared w dt squared at t equals 0. We're going to get 1 over 625. And then remember, we're plugging in our w, not our t. So at t equals 0, our waste is 1400. And so we are going to get 1 over 625. Move this down a little bit so I've got some room. 1 over 625 times 1100. And I'm not going to worry about reducing that. I'm just going to call it 1100 over 625. The only thing I really care about right here is whether or not that's greater than or less than 0. And this, of course, is greater than 0. So what we'll say is, since the second derivative is greater than 0 at t equals 0, the estimate in part A is an underestimate. And we know that because the second derivative is positive, which tells us this is concave up. That would mean that the tangent line lies below the graph, meaning that any point on that tangent line is going to be below the graph, so we get an underestimate in part B. Part C asks us to solve the differential equation. So if we're solving this differential equation, we need to get this solved for w. So we're going to have dw dt equals 1 over 25 times w minus 300. And here we need to multiply both sides by our dt. So we get dw equals 1 over 25 times w minus 300 dt, but we can't really leave it like that because we need to get the w on the other side, so we're going to have w minus 300. We're going to divide on both sides by our w minus 300. And so we have now separated our variables. We got 1 over 25 dt. And So whenever we do this, we're going to integrate here on the left-hand side. We will get the natural log of the absolute value of w minus 300. On the right-hand side, when we integrate, we're just going to get 1 over 25t plus c. Now, if you'll notice up here, it asks us to find the particular solution, w equals w of t. This means to solve for w. So they don't want us to leave our answer like this. Our answer needs to be solved for w. So to do that, we would first need to do e to the on both sides to get rid of that natural log. So we'll have w minus 300 equals ce to the, I'm going to call that t over 25. And then we move the 300 over to the other side. So we would have w equals ce to the t over 25 plus 300. Okay, so this is our general equation, but we still have a c, and this asks for a particular solution. We know the initial condition that w of 0 equals 1400, so we're going to plug in 1400 for our w, ce to the 0 over 25 plus 300. So we get 1400 equals c plus 300. We're going to subtract our 300. And so we get 1100 for our c. Finally giving us our equation, w equals 1100 e to the t over 25 plus 300 for our solution to our differential equation.